Alrighty, in this video we're going to continue with section 2.5, the transformation of functions. And we're not going to be able to finish it in this video, so there will be one more to go after this. But let's get this party started. This time we're going to look at reflecting a function across the x-axis. So here it says the graph of y equals negative f of x is the graph of y equals f of x reflected about the y-axis. And if you think about it like this, here is our y value, the y coordinate of any given point. And if we take that and we negate it, that's just going to flip it across the x-axis. Like here we have this point on the parabola, 2, 4. If we make the y coordinate negative, now it's 2, negative 4. We've flipped it over the x-axis. Same thing over here. We have a negative 2, 4. If we take that y value and change its sign, negate it, it's now going to come down here and be negative 2, negative 4. So every point that was above the x-axis is now below the x-axis. And on the other hand, if we had maybe a function that looked like this, if we had points that were above the x-axis, they would of course be reflected now below the x-axis. And if we have some points that are already below the x-axis, they would be reflected back up above the x-axis. So here in example 4, we're going to reflect a graph about the x-axis. So first, let's graph the cube root of x. Cube root of x. See, if I plug in 0, the cube root of 0 is 0. 1, the cube root of 1 is 1. My next perfect cube on the x-axis would be 8. The cube root of 8 is 2. So it's sort of like we got a parabola laying on its side, and it's pretty stretched out. Whoa, that's a little too far. And it looks something like that. And we can cube root negative numbers. The cube root of negative 1 is negative 1. And the cube root of negative 8 would be negative 2. So here's our graph of f of x equals the cube root of x. And if we know what that one looks like, it's very easy to graph the negative cube root of x. I'm going to reflect that about the x-axis. So the origin's not going to change. But this point that was at 1, 1 is now going to, it's still going to have a positive 1 x coordinate, but now it's going to be positive 1, negative 1. This point got moved under the x-axis. Same thing way out here, this point 2, 8. Well, now that point, I'm going to switch the sign of the y coordinate. Now it's positive 8, negative 2. So here's part of our graph. And now this part of the graph that was underneath, I wonder if I can do it like this. Yeah, just going to flip it up. So now this piece is going to be up in the third quadrant. So here this point was negative 1, negative 1. Now it's negative 1, positive 1. This point here was negative 8, negative 2. Now it's negative 8, positive 2. Everything has been flipped across the x-axis. And there's our graph. It's also possible to reflect about the y-axis. So if we have the graph of f of negative x, now we're negating the x values before we put them in. That graph is the graph of y equals f of x reflected about the y-axis. So for each point x, y on the graph of y equals f of x, the point negative x, y is on the graph of y equals f of negative x. Back to this one, I said an easy way to think about it is to take your y coordinate and change its sign. So this positive 4 became a negative. This positive 1 became a negative 1. Now we're just going to do that with the x coordinates. So let's see what graph they have for us here. F of x is the square root of x. Well, the square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. So our graph is going to look kind of similar to our cubic graph. But will there be any graph over here in quadrant 2 or 3? Can we put negatives into the square root function? No, we can't just plug a negative 3 in here and take the square root of negative 3 because you can't take the square root of a negative number and not get a real answer. But what if we want to graph the square root of negative x? Well, then when we plug negative numbers in, they will become positive. Like if I take this negative 4 and plug it in, a negative 4 becomes a positive 4. So again, in essence, what we're just going to do is change the sign of our x coordinates. This point here was positive 1, positive 1. Now it is positive or negative 1, positive 1. We just changed the x coordinate the sign of it. This was a positive 1, now it's negative. Negative 1, up 1. This point here was a 4, comma 2. Now it's going to be negative 4, comma 2. And our graph is going to look something like this. Again, if I can just grab the graph here I drew here in red, the y equals f of square root of x, I just flipped it across the y-axis. And that's how we got our second graph. We can also vertically stretch or shrink a graph. I'll let you read through all of that, and a lot of it they are just describing what's going on here in this pretty little picture. We see the black graph in the middle. That is just x squared. Well, what if we start putting numbers in front of x squared? That means we'll plug an x value in, we'll square it, and then we'll either multiply it by a whole number or maybe a fraction. Well, if it's a whole number, that's just going to make the graph climb faster, higher. So I move down a bit. Here is 2x squared. Like a good example, if I just plug in 1 into x squared, 1 squared is 1. And that would be my height on the y-axis, 1. But when I multiply it by a whole number, it's going to make it go up even faster. Now it's going to multiply it up by a 2. So we see this blue graph is still a parabola. It has the general shape of a parabola, but it is tighter to the y-axis. It's climbing much faster, much quicker. We can also stretch it out by multiplying by a fraction. Put a fraction in front of that x squared and it starts to flatten the graph out. It still has the parabolic shape, but now the purple graph is the half x squared. Again, the black one in the middle is x squared. If we put a whole number in front of it, we get tighter to the y-axis. If we put a fraction in front of it, we are moving away from the y-axis. But again, we still keep that general parabolic shape. So here in the book definition of stretching and shrinking graphs, let f be a function and c is just some positive real number. If that positive real number is greater than 1, if it is not a fraction, the graph of y equals c times f of x is the graph of y equals f of x vertically stretched by multiplying each of its y coordinates by c. If c is a fraction between 0 and 1, a positive fraction or decimal, then the graph of y equals c times f of x is the graph of y equals f of x vertically shrunk by multiplying each of its y coordinates by c. Again, the idea is the y coordinate is going to get multiplied by that constant, whatever that constant is. And does anybody have a question? Ooh, here's one. Does vertical stretching or shrinking change the shape of the graph? Yes, a vertical stretch moves the function's graph away from the x-axis. A vertical shrink compresses the function's graph toward the x-axis. The other transformations we have discussed, vertical shifts, horizontal shifts, and reflections, change only the position of the function's graph without changing its basic shape. So let's see what we got here. On the left, I'll use red. We're going to graph f of x equals x cubed. Well, let's see. 0 cubed is 0. 1 cubed is 1. 2 cubed takes us to 8, and then we're off the graph. So this part, ooh, that's not very good. This part of it in the first quadrant is going to look like this. And we can cube negative numbers. Negative 1 cubed is negative 1. Negative 2 cubed is negative 8. And here's the other piece of that graph. Now let's see what happens in the second graph. Now we have, oh, and let me label some points here. 1, comma 1. This point up here was 2, comma 8. Back here in quad 3, negative 1, negative 1. And the last one here, negative 2, comma negative 8. Okay, now to go back and recap, it says here we're going to take the y coordinate and multiply it by the constant. And since our constant here is a half, that means we're going to cut all our y values in half. So over here, 1, comma 1 now becomes 1, comma 1 half. This point was 2, comma 8. Now we cut the y value in half, 2, comma 4, over 2, up 4. Let's see if we had 3 cubed to be 27. Half of that is well above 8, so I guess we won't get any more points there. So we did sort of pull this graph down toward the y-axis. Same thing's going to happen in quad 3, negative 1, comma negative a half, and negative 2, comma negative 4. Again, this isn't the best graph, I guess, to see that. You see most of the action is occurring around here, closer to the origin. You see we sort of flattened it out. You know, here it was never getting really flat. It was staying kind of steep. Now we've sort of flattened it out a little bit more in the middle. Take this and apply it to your y values. Multiply by that. You know, so here we cut our y values in half. All these points got knocked down halfway to the y or the x-axis. We can also stretch and shrink on the horizontal axis. So f is a function, c is a positive real number, just like in the last one. If c is greater than 1, if it's a positive number that's not a fraction, then the graph of y equals f of c times x. Notice now the constant is in here with the x. It's not in front of the function itself. The graph of f of c times x is the graph of f of x horizontally shrunk. We divide the x coordinates by c. So here in this picture here, if our c value in there with the x is a whole number greater than 1, we are going to push it closer to the y-axis. If, on the other hand, c is a fraction or decimal between 0 and 1, then the graph of y equals f of c times x is the graph of y equals f of x horizontally stretched out when we divide the x coordinates by c. So again, if we have a fraction or a decimal, it's going to stretch our graph out. The lighter blue one is the original f of x graph. The purple one is c times x, the f of c times x graph. And it looks like we have another great question. How does horizontal shrinking or stretching change a graph's shape? A horizontal shrink compresses a function's graph toward the y-axis. A horizontal stretch moves it away from the y-axis. And I'm sure we're going to see that here in example 7. Now this is a weird one. They don't actually give us a function like a parabola or a straight line or anything. They just give us some key points on it. And it says here, use the graph of y equals f of x here on the left to attain each of the following graphs. So we're going to do these separately. First, let me see what I got here. Okay, there's the graph for b. Here is our original function, negative 4, 0, and then we have a peak at negative 2, 4 through the origin, and then we have a couple line segments right here. Okay, now let's think through this. We have a whole number, not a fraction, not a decimal in front of our x. And what does that tell us it's going to do? We are going to divide the x coordinates by c. We're going to push everything closer to the y-axis. So let's just look at this as a point-by-point basis. This point here got moved halfway toward the x-axis. You know, our c value here is 2, so we take the x-coordinate, divide by 2. Half of negative 4 is negative 2. The point up here, this negative 2 comma 4, I got to cut that x value in half. Half of negative 2 is negative 1, and we're still at that same height of 4. Origin 0, 0. We divide or multiply either of those coordinates by anything, and it still stays the origin. So I guess we can do this part of the graph right now. So what I did, if I trace over this in red, all I did is hit this, and I moved everything halfway toward the y-axis. I scrunched it up a little bit, so to speak. Let's keep going. 2 comma negative 2. Again, cut the x coordinate in half. So that's going to be 1 comma negative 2. And this point 4 comma 0, cut that x coordinate in half. That'll be 2 comma 0. And we have our little triangle underneath the x-axis there in quadrant 4. So there's our function, or the graph of f of 2 times x. And we did that one without a function. We just did it by points. Let's check out the other one. Now it is a fraction. This x coordinate here, negative 4. What happens when you divide a whole number by a fraction? How many halves are in 4? Or you might want to think about it as divide a fraction by a fraction. We invert and multiply. So I'm going to bring the denominator up, flip it over. Dividing by a half is like multiplying by 2. So I'm going to take all of my x coordinates and I'm going to multiply them by 2. Okay, this one's going to get taken off the graph. This negative 4 is going to go out to negative 8. So let's see, here's negative 5, 6, 7. I'm going to put my negative 8 about over here on the other graph. This negative 2 divided by a half is negative 4. So now that point is negative 4 comma positive 4. The origin, of course, again, does not change. So now we have this part of our parabola. Now it's getting stretched out. It's almost looking like half a circle. Again, the origin doesn't change. I'm going to take this x-coordinate and double it. I'm going to move it that much farther away from the y-axis. So instead of 2 comma negative 2, now it's 4 comma negative 2. And there's our first straight line segment. This one will also get pushed off the graph. This 4 gets doubled. 4 divided by half is 8. So that's going to take us right to about here. And I'll connect the line. So fractions stretch you out. Whole numbers scrunch you up when you're in here messing around with the x in that function. All right, time for some practice. Here's a few for you to do. Checkpoint 4, 5, and 6. So you're going to take a basic graph that you know and either flip it over the x or the y or stretch or shrink it. Pause the video and then try the problems and fire it back up and see if you got them. All right, the first thing we got to remember here is how do we graph the absolute value of x? Well, that's going to be a V shape or a check mark shape. You just take any number and you make sure it's positive, and that, of course, is going to go diagonally through the graph paper. And if we plug in negative numbers, the absolute value bars make them positive. So here's our parent graph. Now we're going to do this to it. And what the heck does that do? Notice the negative is not in there with the x. If we write it as, f of x equals something, this is a y-coordinate. That is our height on the y-axis. If we negate what is over here, that's just going to change the sign of our y-coordinates. So every y-coordinate over here is now going to be flipped down to its negative counterpart underneath. This is a reflection across the x-axis. So the origin will not change, but all of these points are going to get reflected to their negative counterparts in the lower two quadrants. So it turns our absolute value graph upside down, reflected it across the x. Okay, and let's see what's going on here with this function. Oop, guess I got to move that up a little higher. We're going to do something with the cube root function. Let's see if I can squeeze both of these in there. Yeah, good enough. I'll work on the left first in red, and we've seen this graph already in the examples. Cube root of x. Cube root of 0 is 0, cube root of 1 is 1. The next perfect cube would be 8, and its cube is 2. So there's our first quadrant piece of the graph. And then cube root of negative 8 is negative 2. There's the other one. Now let's see, we did the example where we put the negative outside the cube root. I can't remember exactly what example it was, but we did the cube root of x, and then we did the negative cube root of x, and that was a reflection across the y-axis. Now the negative is under the cube root. It's under the radical with the x, not outside. Here we're negating the x and then we're cubing it. Here we cubed the x and then we negated the answer. So this is going to be a reflection across the x-axis. Across the y-axis. I'm going to take all my y values and change their sign. So let's see here. This point was 1, 1, or excuse me, we're going to change all the x coordinates signs, not the y coordinates. So here was 1, 1. Now on our reflected graph, it'll be negative 1, 1. This point here was 8, 2. Now it's going to be negative 8, 2. We switch the signs of the x coordinates. In the last one, we switched the signs of the y coordinates. And then our graph will continue here at 1, negative 1, and 8, negative 2. And there's our transformed graph. Now it looks like we have a vertical stretch or shrink. The first function, our parent function, is the absolute value of x. That starts at the origin and goes diagonally through the graph paper boxes. Everything's positive in the absolute value function. And now we have this 2 in front of the absolute value of x. And remember, when we put a whole number out here, that's going to move us closer to the y-axis. We looked at the parabola picture, the parabola example here. Absolute, or the x squared was the black graph. When we put a whole number in front of it, it made things rise faster, because whatever the output was here for our y-coordinate, we doubled it. So it made us go up quicker, and that moved us closer to the y-axis. Oops. And that's what's going to happen here. This was the point 1, 1, 2, 2, 3, 3, and so forth. Now everything's going to get moved closer to the y-axis, so we're going to double, we're going to multiply all our y-coordinates by 2. Again, this was 1, 1. Let's just pick out a couple of them, and 4, 4. Actually, we can't go that high. The graph won't allow us, so let's do 3, 3. We're going to double our y-coordinates. Instead of 1, 1, this is going to be 1, 2. And we have our origin. We could draw our line right now. Or let's do 3, 6. Double the y-coordinate. Over 3, up 6. And of course, on the other side of the y-axis, we'll have those pretty much same points. So it's going to look like this. Again, we moved our absolute value graph closer to the y-axis because that was a whole number. If that had been a fraction, let's just say a half x, it'd be more like this. Oop, I was supposed to change over to a different color. If we had a fraction instead of a whole number, our graph would move away from the y-axis. And it looks like we got one more to go here. Here is our parent graph, so to speak. And why did I put 2 of these on here? Okay, I guess, yeah, we got to find a f of 2x and f of 1/2 x. So now in the previous example, we were messing around with the y-coordinates. We were multiplying our y-coordinates by this number. Now we are going to be dividing by the number in front of the x. So for example, in this first one here, we have a 2 in front of our x, so we're going to divide our x-coordinates by 2. And I wish, let's see here, I guess I can move this over. We'll just do these one at a time. I'll make the graph a little bigger. There we go. So we're going to cut all our x values in half. All x divided by 2. So this x was a -2 divided by 2 will be a -1. The y value does not change. Here, this x-coordinate is a 0. 0 divided by 2 is still 0, and we stay at the y of height of 3. We cut this x value in half. That's going to be 1, 0. Cut this x value in half, 2, -3. Cut this x value in half, -3, 3, 0. And we connect the dots. And there's our graph. The whole number scrunched us closer to the y-axis. Here we have a 1/2 that's going to stretch us out in the next graph. And let me just do this one right on top in red. Let me do this. So when we divide by a half, it's like I'm multiplying by 2. I'm going to double that x-coordinate, -4, 0. 0, 3, doubling or cutting in half. This does not change. That point's going to overlap. And let's see here, this 2, 0, we double that x-coordinate and it becomes 4, 0. And this x-coordinate doubled becomes 8, -4. And then it looks like we're going to go off the graph. Oop, get back there. 8, -4. And then we're going to go off the graph. If we double that, it would be 12. That's going to even take us off my screen. So I'll leave my line looking out like that. And I'll connect these dots. So the red line, we put a half in front of the x inside the function. The black graph, we put a 2 in there. We doubled it. Bigger numbers crunch us up to the y-axis. Halves and fractions and decimals will stretch us out. There's some problems for you to try. If I believe for this section I might have printed out some special graph paper just to use on these certain homework problems. So if you missed class, remind me to get you some of that.